Hello everyone, welcome to the course on computer aided drug design. We will continue on the topic of QSAR, that is quantitative, structure, activity, relationship. What is this? QSAR is just nothing but a mathematical relationship between the biological activity, that's the experimental data, or we can collect it from the literature of a molecular system and its geometric, physical, electronic and chemical properties. So the dependent variable will be the activity and the independent variable will be a parameter, descriptor of structural feature. Okay, it could be a geometric activity descriptor, a physical descriptor, or electronic descriptor, or a chemical property. So it could be any one of them. Okay, it could be any one of them. So there are a lot of descriptors available in the literature. We will talk about some of them as we go along. So basically you are developing a mathematical relation, a linear regression or a non-linear regression. So the property are called the independent variables, okay, or sometimes we call it X, and the activity is the dependent variable, we call it Y. So if you remember your statistics, you will get Y is equal to function of various X's. Okay, so the descriptors could be physico-chemical descriptors like your shape, size and so on. Electronic descriptors, electronic features, steric descriptors, volume, lipophilicity, solubility, how lipophilic it is, log P, hydrogen bonding capabilities, okay, number of hydrogen bond formation, shape, charge, polarizability, so many descriptors. Thousands and thousands of descriptors can be calculated for a molecule. Okay, we started with the electronic descriptors, or it's also called used by Hammett. Okay, dissociation constant of substituted benzoic acid. Okay, these are called the substituted benzoic acid, and these benzoic acid can dissociate. Okay, you have a dissociation constant and then they dissociate into the acid form COOH and COO minus and so on actually. Okay, that is the substituted benzoic acid. Now depending upon the R group and depending upon the position, ortho, meta, para, you can have different dissociation constants. That's what this table gives. As you can see, fluorine, if it is in the ortho, okay, ortho, it has a very high dissociation constant. Okay, whereas when you go down to CH3 type of group in the para, okay, here you can have a very low dissociation constant, as you can see, right? So depending upon the position, you can have and the type of group, you can have different dissociation constants. Okay, so electron withdrawing or donating, which stabilizes the anion, that is called the anion. COO minus is called the anion. Okay, so electron donating groups. Okay, the electron donating groups we have are then OR, OH, they're all electron donating group, whereas electron withdrawing groups we have here X could be a chloro, bromo, ido, then CO, CHO, COOH, CNNR. These are all electron withdrawing groups. Acid form is stabilized if R is electron donating. So all these groups, so this is the acid. Okay, this is the acid form, this is the anion form. So the acid form is stabilized when we have electron donating group. Okay, the anion form is stabilized if R is electron withdrawing group. So if the electron is withdrawn like X and so on, you get the anion. Okay, whereas acid form is formed when you are getting electron donated like O's, R, O, CH3, OH and so on. If anion form is stabilized, then you are going to have a large K. If the acid form is stabilized, you are going to have a small k. Okay, so log Ka minus log Ka and substituted. Log Ka substituted, that is called sigma. Okay, that's called sigma. So why does all these things come into picture? If you look at the antibacterial activity of sulfonylamides, okay, these are called sulfonylamides. They got a sulfur group and they form N minus and H plus here. Okay, depending upon the R, either you will have this or you will have the anion form. The anion form or this form. Okay, but the anion form is the active antibacterial agent, not the neutral form. Okay, because if you look at the para-aminobenzoic acid, which is the substrate for bacteria. Okay, and this drug, sulfur drugs, also look similar to that. So there is a competitive inhibition that's happening, and hence the sulfur drugs act. Okay, so the anion form is the active part, not the neutral form. So that means we need to have this dissociation taking place. So depending upon the R, like we saw in the position of the R, either the anion or the neutral form is stabilized. So if you have a very high sigma, okay, you have log 1 by C also going up. That means the activity. R stabilizes the anion by electron withdrawal, thus increasing biological activity. Okay, whereas if you have electron donating, then the biological activity goes down. Okay, if the electron withdrawing, we have the biological activity also going up. Okay, this is with respect to the electronic feature. Now let's look at the other one, that's called the steric feature. If you look at the hydrolysis of esters, this is an ester, RCOOCH3, R could be anything. Hydrolysis means water is acting, so you need a catalyst or an enzyme or something like that. So it forms RCOOH, that is the methanol, okay, methyl alcohol. So the size of the R affects the rate of reaction, because what happens is there is a nucleophilic attack on the carbonyl carbon here. So the R, okay, there is a nucleophilic attack here, okay, which leads to the formation of RCOH as well as the C3OH here. So the size of the R tells you how easy is the nucleophilic attack or how difficult it is. If the R is very large, it's very difficult for the nucleophilic attack, so the activity goes down. If the R is small, activity goes up. This is called steric effect, or this is also called Taft parameter. This is calculated by log K of RCOOCH3 minus log CH3COOCH3. Okay, K is the rate constant for ester hydrolysis. Okay, so larger it is. Okay, so we have larger the R, lower will be the rate constant. Okay, why does this important? If you look at acetylcholine esterase, there are inhibitors for acetylcholine esterase. So hydrolysis of this acetylcholine takes place here. Okay, it attacks here. Okay, so organophosphates must be hydrolyzed to be active, and their biological activity depends upon the size of this group, the size of the leaving group here. Okay, so the activity is directly proportional to this size of the leaving group, or it's also called a Taft parameter. Another descriptor which is very, very important is the log P here. Okay, that's the log P. Absorption and distribution process in biological systems are determined by the hydrophilic, hydrophobic properties of molecule. We looked quite a lot about this log P. Log P is nothing but in octanol divided by in water, a partition of this particular molecule. Okay, more in the octanol, that means we call it hydrophobic, less in octanol, more in water, we call it hydrophilic. So many processes depend, and as you can see, the depending upon the substitution, each substitution contributes towards log P. For example, CH3 is 0.56, that is more hydrophobic. If you have say a tertiary, you have 1.98. okay, aryl group 1.96, C6H11 2.51. okay, whereas if you look at nitro, OH, NH2, they all negative because they are more hydrophilic. So if you have a molecule, if you substitute with a particular functional group, we can find out the contribution and either subtract the original log P of the parent compound or add the log P from the parent compound. Okay, so log P plays a very important role. For example, if you look at anticonvulsant activity of a diverse series of drugs. Okay, these are the series of drugs we are talking about. you have R1, R2 groups here, and then we have X here. X could be NH, CH2, O, CO, NH2. Okay, this is a 5-membered ring. So the activity of these drugs, these are anticonvulsant drug. Okay, they all depend upon the log P here. As you can see, more hydrophobic, more is the log P, activity will be more. Okay, so log P plays a very important role. We will look at log P more in detail because it plays a very important role, because the absorption through GI depends on log P, as we saw long time back. So if you look at drugs which bind to serum albumin, okay, so as the log P increases, because as it becomes more hydrophobic, activity also increases. This is the QSIR, this is the regression relation. So as the log P increases, and this is a linear regression relation, as you can see here, activity also increases this way. It need not be all the time linear. Okay, so greater for hydrophobic drugs. Okay, binding increases as log P increases. It need not be all the time linear. It can be like this also. There could be an optimum log P 0, when the activity is max, and initially it increases, reaches a max, and then comes down. So generally for anesthetic activity of ethers, it's followed like this. So it's a non-linear relation. So the regression relation could be non-linear. As you can see, again it depends on log P, but it is log P square and log P. So we have a non-linear regression relation. Okay, so we have a constant term here, and then we have a square term for log P here, and then we have a linear term for log P. So the relation will go like this. It increases initially, okay, because of this it increases fast. As it goes to a large log P value, this term starts taking place, so the log P starts coming down. Okay, so this is a optimum log P when you have the maximum activity. This is applicable for ethers only, anesthetic activity. So you can have systems where this type of behaviors may be observed. Okay, so this is called the optimum value anesthetic activity. Okay, so hydrophobicity applies quite a lot actually. One thing you need to remember is QSI equations are only applicable to compounds the same structural class. Okay, don't forget that. I perform a QSAR for one class of compounds like benzoic acids, and then I try to extend it to some other diaryl systems. It might not work actually. Okay, so for different structural classes also, interestingly, the optimum log P that is given here, the optimum log P given here seems to be 2.3. So around that 2.3 you may get very high activity for many of these structural classes also. Interesting. Okay, structures with log P around 2.3 enter CNS, that is your central nervous system. As you remember, blood-brain barrier entry, we need approximately 2.3 for it to enter. If it is lower, it's a bit hydrophilic, so it might not enter at all. Okay, so for many classes of anesthetic drugs, even though you may have different types of graphs, okay, so approximately the log P comes out to be approximately 2.3. okay, this is a very important point you need to keep in mind. Okay, it's very useful to keep in mind. Barbiturates, they have a log P approximately 2. Okay, so this number is quite interesting. So if you want to avoid CNS side effects, we need to be away from 2, so that it comes either down or down here, so that it doesn't pass the blood-brain barrier. Okay, so we looked at electronic effect. The constant is called a sigma, that's called the Hammett substitution constant. Okay, that is the measure of the electron withdrawing or electron donating influence of substitutions. Sigma for aromatic substitutions measured by comparing the dissociation constant of substituted benzoic acid with benzoic acid. So sigma is an ratio of you can find out the substituted versus unsubstituted. Okay, and the dissociation constant is given by PHCOO minus divided by pH COOH. COO minus means anion form, COOH is the acid form. We have read that long time back. Agreed. So the sigma X, we have the electron withdrawing group, for example NO2. Okay, the charge is stabilized by X. The equilibrium shift to the right. Okay, equilibrium shift to the right. That is Kx is greater than Kh. Kh means substituted. Kx means substituted. So electron withdrawing group. Okay, equilibrium shifted here. Kx is greater than Kh. So this is a sigma is a positive value. Okay, electron donating group CH3 for example. Okay, it's donating. Okay, then what happens? Charge is destabilized, equilibrium shifts to the left. Equilibrium shifts to the left here. Okay, so Kx is less than Kh. Okay, so sigma x will be negative value. This is called the Hammett substituent constant. Okay. Okay, sigma value depends on inductive and resonance effects. Okay, sigma depends on whether the substitution is meta or para. That's also very important. We saw long time back a table where meta and para have different values of dissociation constant. Ortho values are invalid due to steric effects. Ortho means its substitution is so close, so because of steric it might not work actually. Okay, so meta substituent. Look at this. N double bond. This is NO2. Okay, we have the R here. If you have para NO2, sigma is 0.78, meta NO2, sigma is 0.71. Okay, E withdrawing, inductive effect. Okay, when you have para substitution, E withdrawing, inductive plus resonance effect. Okay, because when we have the para substitution, we have there is a resonance that's happening in the nitrogen. As you can see, the double bonds in the benzenes keep moving. Okay, like this. This is called the resonance effect. Okay, so we have this like this. So when the electron is withdrawing, we can have both the inductive and resonance effect. That is para substitution. Okay, whereas in meta substitution we will not have the resonance effect happening, only the inductive effect will be happening, as you can see here. When we have OH type of group, we saw NO2, meta, we have sigma m meta 0.12, para minus 0.37. Okay, there is only inductive effect, whereas electron withdrawing, whereas an electron donating, predominant resonant effect. Inductive effect is minor. So we have resonant effect happening. As you can see, how the double bond gets shifted. Okay, so you have the lone pairs happening here. Okay, so it's minus 0.37. Okay, what does that mean? The neutral form is more stable than the anion form. Here the neutral form is in the meta substitution, the neutral form is less stable than the anion form. Okay, whereas in nitro, meta and para almost the same. Diethyl phenyl phosphates, you have two ethyl groups here. They are all used as insecticides. We have equations like this: 2.282 sigma minus 0.348. Okay, so electron withdrawing substitution increases the activity. So R quantifies a substitution's resonant effect. F quantifies the substitution's inductive effect. Okay, one is called the resonance, one is called the inductive, like I showed you here. If you look at aliphatic electronic substitutions, okay, that is we have the aliphatic group here. So you can have hydrolysis like this. Aliphatic, so we have MEOH is the how does they act? They are defined by again sigma 1. You have only purely inductive effects. They are obtained experimentally by measuring the rates of hydrolysis of aliphatic esters. Okay, hydrolysis rates measured under basic and acidic conditions. So you do not have the resonance happening here. you will always have induction happening here, because unlike aromatic where we have the resonant bonds, aliphatic will not have it. So X electron donating rate goes down because sigma 1 is negative. X electron withdrawing rate goes up because sigma 1 is positive. Okay, understand? So in aliphatic systems there is only inductive effect, there is no resonance effect. We can measure. How do you measure? We can measure by looking at the rates of hydrolysis of aliphatic esters. Hydrolysis is measured under basic and acidic condition. So if you have electron donating, then we have the rate going down. If you have electron withdrawing, pulling, rate goes up. So under basic conditions, rate affected by steric, like I mentioned, steric plus electronic factors. So gives sigma 1 after correction for steric effect. Under acidic condition, rate affected by steric factors only, that is ES. We talked about ES before, right? Taft size factor. So remember that under basic conditions we will have steric and electronic effect. Under acidic conditions we have only steric effect. That is why here we mentioned the sigma L here, because you can have steric effect also coming into the picture. Steric factors, Taft's steric factor we talked about. Let's compare the rates of hydrolysis of substituted aliphatic esters against a standard ester under acidic conditions. Okay, if you bring basic, then you are going to have some electronic effect coming into. Okay, so we can have a kx, log of kx minus log of k0. Kx represents the rate of hydrolysis of a substituted ester, rate of hydrolysis of the parent ester. Okay, limited to substitutions which interact sterically with the tetrahedral transition state for the reaction. Remember that. Cannot be used for substituents which interact with the transition state by resonance or hydrogen bonding. So they will start interfering. The resonance effect and hydrogen bonding, all these will affect your Taft parameter. May undervalue the steric effect of groups in an intermolecular process, that is drug binding to a receptor sort of situation. You also have a term called molar refractivity. It's a measure of substituents volume. This is a descriptor which we can calculate. That's called molar refractivity. It's given by n square minus 1 divided by n square minus 2 molecular weight by density. Okay, this is a correction factor. This is called the index of refraction. Correction factor for polarization. Okay, that's called the index of refraction. So it's a function of molecular weight, function of density. That's called molar refractivity. When you do molecular weight by density, of course, you end up with volume, right? So this is a descriptor which we use many times. Then comes Han's equation. What is Han's equation? A QSAR equation relating various physico-chemical properties to the biological activity of a series of compounds. So you will have log P coming into picture, electronic factors coming into picture, steric factor. Okay, so we can have a QSAR activity on the left hand side which may have terms related to electronic, steric and log P. So you start with a simple equation and you can elaborate it as more structures are synthesized. Log P, you can put it as a parabolic relation like this. Okay? So log P square, log P, electronic term, steric factor, and this is a constant. So typical Han's equation. Okay. Remember QSAR we can develop only when we have some experimental data for activity, that's the left hand side, or we get some data from literature where someone else has estimated the activity for a series of compound. Okay. So look at this adrenergic blocking activity of beta halo. Okay, this is beta halo, beta aryl amines. Okay, these are amines. Okay, aryl amines, as you can see here. Okay, we have the nitrogen here, and that's why we call aryl amines. Then we have the halo compounds here. So typically this is how the Han's equation looks like. Okay, 1.22 minus 1.522 pi minus 1.59 sigma. Phi represents the hydrophobicity, sigma represents the electronic. Okay, so it's a positive with respect to the hydrophobic substituents and it's negative with respect to the electronic factor, that is electron donating substituents. This is called enhanced equation. So the log P related term comes here, the electronic comes here, but there is no mention much about steric information here. These are anti-malarial activity of phenanthrene aminocarbenols. Okay, so we have 3 fused benzene rings. Okay, we have the amino group here, that's why aminocarbenols here, because we have the OH here. Look at them. We have the log P square, log P. Okay, then comes the hydrophobic part of it, and then we have the electronic part of it. Okay, we have 2 terms, one for sigma x and sigma y, similarly for phi x and pi y. Activity increases slightly as log P. Parabolic relation, optimum value for log P value for activity. Activity increases for hydrophobic substituents, especially in ring Y. Here. And then activity increases electron withdrawing substitution, especially ring Y. I think it should be activity increases hydrophobic 5 electronic, yeah, and Y. Okay. Substituents must be chosen to satisfy the following criteria. A range of values for each physicochemical property studied. Okay, so when I synthesize new molecules, I will try to substitute so that I get a different phi. That means different hydrophobic, hydrophilic values. I get different sigmas and so on. Values must not be correlated for different properties. That means they must be orthogonal in value. At least 5 structures are required for each parameter studied. So this is a very important rule of thumb, okay, for each parameter studied. So for example, I'm looking at a different, I'm substituting with H or Me or ethyl or N-propyl, N-butyl. So the phi changes like this. So for H0, so it becomes more hydrophobic, okay. Molar refractivity changes like this. I defined what is molar refractivity before. Okay, correlated values. So we have substituent H, Me, OMe, phi, Mr. As you can see, some of them, there is no correlation in values. Here, okay, there is no correlation in these values. Okay, these are all, whereas they are all correlated. Mr and the pi. There is something called a Craig plot, which is also used in QSIR. Okay, this is a Craig plot. Okay, what is this? We have 2 things happening. One is the pi. We have on the x-axis, okay, pi. That is the hydrophobic hydrophilicity of the substitution. Sigma is the electronic of the substitution. Positive sigma, positive phi. This is negative pi, negative sigma. Okay, so different substitution groups, as you can see, NO2 falls here. It's got a very high electronic and very low pi. If you look at fluoro, very low sigma and pi. If you look at the SF5, sulfur with 5 fluorines, it's got high pi as well as reasonably high sigma. Okay, so this is electron withdrawing. So here we have the electron donating. Here it's more hydrophobic. Here it's more hydrophilic. So if you have say COOH, it's a hydrophilic. Okay, it's a hydrophilic, and then it's also electron withdrawing. If you look here, this is a hydrophilic OH, and it's electron donating. So this is a very interesting plot. So we can decide which substituent to put into our parent molecule for our studies. Do I want to look at electron withdrawing effect by maintaining the hydrophobic hydrophilic balance, or do I want to have modifying the hydrophobic hydrophilic activity nature by maintaining the the sigma. So by deciding, I can synthesize different types of molecules and study their activity, so that I will have a very fruitful QSAR relationship. That's very, very important. Okay, so what is called allow an easy identification of suitable substituents for a QSAR analysis, which includes both the sigma and the pi. Choose a substituent from each quadrant to ensure orthogonality. That's very important. Choose substituents with a range of values for each property. Okay, so I can choose substituents, say from groups here. I can choose from here. I can choose from bottom. I can choose from this. That way I will keep orthogonality. And also I can choose one low, one high, one low, one high, so I can get the range also into the picture. Okay, range of values. So that's the advantage of that particular figure. Then we have something called the Topolis scheme, okay, which can help you to synthesize molecule in a very, very effective way, so that you address both the hydrophobicity as well as the electron features, that is electron withdrawing and electron donating features. Okay, so we will continue this Topolis scheme in the next class. Okay, thank you very much for your time.